you for this session on autonomous utility vehicles organized by the ASEAN Student Chapter of University of Moratuwa. Today, our session will be conducted by Dr. Thanuja Ambegoda, who recently joined our Computer Science and Engineering Department as a senior lecturer and a former co-founder of the Enway company in Germany. I hope you all will participate interactively in this session and gain something new. So, over to you, sir.
Okay, thank you for the introduction. It's a pleasure to be talking to some enthusiastic students on a Saturday afternoon. So I'll be talking about autonomous utility vehicles. I have been working in the industry for the last 3 years in this sector. So what I will be talking about are some general approaches, general principles, and some learnings. I also have looked at the robotics exposure of the audience. I have adapted the talk to that also. And I will not be talking about specific technical details of my former company for obvious reasons, I guess. But there will be lots of interesting things to talk about, and also we can also discuss at the end if we have any questions. Okay. So, autonomous utility vehicles. So when you hear the term autonomous vehicles, usually, wait, let me also do something here. I can have, anyway. Do you see my mic, my mouse pointer, by the way? Oh no, probably now you can see. Great. Anyway, sorry about the interruption. So when you hear about autonomous vehicles, usually you hear a lot about self-driving cars, like companies like Waymo from Google, or Cruise, Tesla. These are not that heard of, although they are coming out in popularity now. So on the top left, this is the kind of product I was working on. This is a autonomous sweeper. So this drives around cleaning the floor of, say, warehouses or outdoor, a public square or a campus. It cleans, and then it comes to a predefined spot that it knows it can dump the garbage. It can dump it and go to even a charging spot. So that's an autonomous sweeper. One example of a utility vehicle. There are also many other examples. When you talk about ground vehicles, there are construction robots. It can be used to move sand or stone or rubble in a construction site. You have weed removing robots. Also a painful or a tedious task in a farm to remove weeds. So it's great if we can automate it. And this is even run by solar power. You also have harvesting robots. So this can pluck ripe apples, can drive through these lanes and then look at the trees, pick the ripe ones, put it in the container. So another utility. Another very commonly used, an area where you have autonomous robots is mining. So this can be either used for transporting stuff from the bottom of the mine to the top, or the other way around, or even taking crucial measurements like, let's say, the oxygen level, making a map of the mine, or humidity level, things like that. So these are just ground vehicles. There are two other sectors, like we have flying machines like drones that are utility robots. There was one article recently about this drone that can spray pesticides, I think from the University of Pennsylvania. Then there can be swimming robots also, underwater robots. The principles are actually the core principles are quite similar. There are obviously some changes, and when it comes to ground vehicles, the core principles have even more overlap. So I hope we can cover some interesting areas in this next half an hour or so. Right. So how do you build such a system? What kind of things do you have to put together? What things you have to take care of? So in an intelligent machine like a robot, the brain of the robot is the computer, right? The legs or the wheels are represented by the drive unit. And one obvious connection is this interface. So you need to have this drive-by-wire interface to drive the motors using the commands generated from the computer. There are interfaces like the CAN interface, um, which existed before robotics. But yeah, this is one important aspect. And this is a low-level communication, but it can also be wrapped in drivers where you can work with easily. Apart from that, another major area is the set of sensors. So that's how the robot sees the dynamic environment that it is in. We will go into details, into the details of the sensors in the next slide. Then you have to work on the hardware drivers and controllers. For example, some actuator like the fruit plucking robot has this robotic arm that goes to the apple or whatever the fruit, grabs it and puts it into the container of the robot. And you need to be able to make them communicate with the computer. So you need to sometimes have the drivers written by yourself, depending on what the vendor gives you. Another huge area is the safety system. I will talk about this at the very end. Okay, so this is the hardware architecture. The general hardware architecture I can see in many vehicles across all these domains that we talked about before. By the way, if you have any questions, feel free to just maybe speak up. Maybe I'll also receive a notification, but also feel free to speak up. I actually have not done the Q&A part in Zoom yet. Anyway, moving on, the sensors. So there are so many types of sensors and they have their strengths and weaknesses. So it's important to understand these things. And usually when you design a robot for a real life application, it's a combination of sensors that you have to put on the robot. It's very rare that you have just one sensor. I did hear about an autonomous tractor running on a farm. So it's an empty field and it only uses GPS. That was a long time ago. It was like an experimental project, but that's not possible. What if a person comes in front of the tractor? The GPS cannot tell that, right? So you need to have all these kind of sensors, and it's important to know what a sensor can do and what it cannot do. I'll start with the most commonly used sensor. I think you can find this in almost every robot that moves. So this is an IMU, the inertial motion unit. The main output it gives is the acceleration in all the directions. So the 3D vector for acceleration. So as you remember from calculus, when you integrate acceleration, you can get the velocity. When you integrate the velocity, you can get the displacement. So in theory, a perfect IMU can tell you where the robot moved accurately, in theory, if the IMU is perfect. But the bad news is that IMUs are far from perfect. It's very noisy. It can give some direction, some indication of where it has moved, what speed it moved, or what acceleration it moved. But one big problem is the accuracy becomes worse over time. And it's not perfect to start with anyway. So that's why we have other sensors. So when it comes to self-driving cars and most autonomous utility vehicles, a very common sensor is the LiDAR sensor. So LiDARs are laser ranging based sensors. It basically gives a 3D scan of the world. So each point represents a point on a real world obstacle. the coordinates of it with respect to the sensor. You could build a 3D representation of the world easily with readings of such a sensor. There are different vendors. The prices are quite high. It's probably the most expensive sensor we have to work with. But the good news is the prices are falling. So it's getting easier for startups to leverage this very useful technology. This is, by the way, by far the most accurate sensor if you want to detect obstacles or if you want to build a map. That's the go-to thing, and it's also very fast to get it running and get some kind of robot moving, and that's what we did also. Let's move here. So these are cameras. Cameras are probably the most common thing. You have also heard cameras. You have worked with cameras. There are types of cameras. This is just monocular single lens. This is a 3D camera. So this gives a 2D view of the world. The usual cameras give a 2D view of the world, as you know, like photos. But there are depth cameras that can give that it computes the 3D view of the world based on multiple lenses, and also a projected, in this case, an infrared beam. Yeah, they're also getting much better in quality. Especially in the last year, I have seen quite tremendous improvements of the quality of the data being returned by these sensors. Radars are very commonly used in cars. It's the best way to get the speed of the car in front of you. It's when you're driving on a street, that's one critical information you want to have. How far is the car in front of me and at what speed it is going, or at what speed it is coming at me, right? In the worst case scenario. Right, these are used especially when you're driving fast. But some robots, if it's a slow-moving robot in an environment where there are not fast-moving vehicles, you might not use it. But it works quite well. These are ultrasonic sensors, very similar to radar, but works with ultrasonic waves instead of radar waves. As you probably have experienced, they are very commonly used in cars as parking sensors. The accuracy is quite low. It can tell, okay, there's something in this next 1 or 2 meters, but cannot say in centimeter level. As opposed to LiDAR sensors, it has centimeter level accuracy, even 1 or 2 centimeters. Cameras, it varies the accuracy. If it is closer, like within 3 meters, maybe it's quite high accuracy, but when it goes beyond some limit, it gets worse. And usually LiDARs have 100 to 200, well, it's 100 meters of range, and cameras have much less when it comes to accurate readings. But you can have a camera, to see further away. If you just want to see if there's a building or if there's a car somewhere, it's perfectly fine. If you want centimeter accuracy readings, LiDARs are your go-to sensor. Okay, that was quite a bit about sensors. It's an important subject to worry about. You have to be on the watch out of developments, new sensors coming, new companies popping up. So if you're in the industry, it's something you have to look into almost, let's say, every week, if not every day. Okay. So let's move to software now. Let me have a sip of water. Okay. I've heard that you have already had a couple of sessions covering ROS, the robot operating system, which is a very common base framework to write robotic software. So I will not talk about it. I assume you have heard of it, but you can also have a look after the talk. There are different, there's ROS 2 now. I think one thing I can tell is that ROS 2 is becoming more advanced. People are adapting it much more. But I would still recommend, if you are starting with robotics, start with ROS 1, the initial version, at least for a month or two, understand the principles, understand the ecosystem. And then when you launch a bigger project, ROS 2 is nice, but make sure you know the fundamentals of ROS 1 before that. And ROS 2 is definitely better than ROS 1, I think. I think one can debate about it, but there are so many benefits when it comes to safety, when it comes to real-time guarantees, which are very important aspects when you have real-life robots. Anyway, okay. The next points I'm covering in the next few slides. So these are I think the most important principles. So in any robotic textbook, I think you can find these things. And obviously when you build a robot, you have to work with all these concepts. I will be not going into deep, as I said, but I will talk about it enough, let's say, right? Okay, we'll see. Okay, localization and mapping. You might have heard the word SLAM, simultaneous localization and mapping. It's related. Let's talk about mapping first. So I think everybody has used Google Maps. It tells you where things are. It tells you where you can walk along, where there are buildings. It helps you to plan your route from A to B. So that's the map. And a robot also needs a map. And there are different ways of building a map. So on to your right is a 2D representation of a map built for a robot. These black lines show the walls, so you obviously cannot drive through walls. Maybe here you have a table or a column in a building, so you cannot drive into it. So the black you have in black you have the obstacles you have to avoid. The gray is the free area. So this is a static map of obstacles. It does not contain the people who might be walking around, but it's already a good idea if you want to drive around, right? On the left, this is a GIF I got from Cruise Automation. This is a 3D map built using LiDAR scans. So each point is from scans of a LiDAR. So you can see trees, you can see buildings. This is a 3D representation. And the way you build such a map is you drive around with the robot, or maybe you have heard of the Google backpack with the LiDAR on it. Either way, the idea is to collect some sensor measurements by exploring the area. So once you have recorded the sensor measurements, you could run it typically on a server. It's an offline process. You run some algorithms, you compute overlaps between scans, you have some other constraints. There are very nice open source packages to do these things. The end result is a 3D map that you can use for the robot. There are two uses of the map. One is having the static obstacles, helps you in path planning. The other one is to localize yourself while driving. So what's localization? The robot should know where it is on the map. So based on the features on the map, let's say there's this tree here, there's this building here. And when you are driving, you have the sensor. You have the sensor readings, the laser scans. You match the laser scans you're having now, the current laser scans. You match those with the ones, with the features of the map. By matching those two, you can figure out where the robot is on the map. So that's localization. The critical aspect is that it has to happen fast enough. Fast enough is defined by how fast the robot is going and how dynamic the environment is, right? So for a car, it has to happen quite fast. Even if it's a slow robot, if something is changing rapidly, we had once a case where the shelves were changing in a warehouse. They literally change the location. So you have to take into account the changes and rapidly output the current location. That way you have the accurate current location. Otherwise, path planning will not work. I hope that part was clear. I think I was talking a bit too much about that. So once you have a map, when you want to get things done, you need to figure out how to go from point A to point B. Could be a cleaning robot. This is a cleaning run. You have to define a path. So to know the path, you get the static obstacles from the previous part from the map. And then by knowing what's the free area, there are several algorithms you could use to figure out the shortest path, if that's what you're concerned about. I'm saying that because it's not always what you want. If it is a delivery robot, a warehouse robot that transport things, you want to have the shortest path. If it's a cleaning robot, it has to maximize the cleaning coverage. So it goes like a serpentine pattern, make sure everything is clean. It goes on to the end point. Either way, you need to have a path plan. So path planning is also a very interesting area of research. There are also nice open source packages you could use off the shelf. But both in the case of SLAM packages for using localization and mapping, as well as path planning packages, there are open source solutions, but almost always you have to understand how things work. You have to change the hundreds of parameters they come with if you want to have an effective result. For some demo, it's fine, but if you want to deploy a commercial product, you need to understand a lot more. And usually people end up, so in our case, we ended up developing our own path planning algorithm because this was a sweeping robot and there were no open source products like that. And yeah, we just developed our own. Okay. Moving along to the next part now. Okay, one more thing maybe in the previous two. Mostly these algorithms are rule-based. I'm saying this because for object recognition and detection is slightly different. So what is object recognition and object detection? So to see if there's an ambulance, that's recognizing an object. To see where this ambulance is on the street, that's object detection. So detection is the place, the recognition is what the object is. And both are important for a robot. So in the case of driving, yeah, you need to give way to an ambulance. For a apple plucking robot, it needs to see the apple, detect the ripe apples, recognize the ripe apples, detect the location of the ripe apple, and then it can pick the apple. So this is a very important aspect, a very important component of utility robots, because it's about getting things done, and to do things, you need to know what and where of many objects, right? The best algorithms we have now are deep learning based algorithms. So YOLO is one. There is, I think, YOLO version 4 even now. It works quite well off the shelf, but if you want to train it for particular cases of objects, let's say different types of garbage, for example, something with it, you have to, adapt it to some retraining. There are many other algorithms now, even potentially even better than the one I'm showing now. So yeah, this is where computer vision comes in a lot. Very important and very widely researched area. There are so many papers every year in many conferences on these topics. This also has to happen real time almost, like very fast. So that's a challenge. You typically don't have access to a cloud server. You need to do it on the edge. That's the term you use when the computation happens on the machine itself, like on an onboard computer or a mobile phone. So that's the edge AI, kind of a buzzword these days. So you need to have algorithms that work fast, not resource intensive. And accurate enough. And these are not easy things to trade off. Yeah, and that's obviously the challenge. Okay, I'll have another sip of water. Right, so when it comes to a field robot, a utility robot, there are different scenarios it has to face, and it has to react differently. So in the case of a sweeping robot, it has to know if the tank, if the garbage tank is getting full in the middle of the cleaning run. It has to identify, okay, the garbage tank is getting filled. Then it has to figure out the best path to the garbage dumping site. It has to go there, dump it, and then come back to the spot it was before, and then continue cleaning, right? That's what a human does. But we do it instinctively. We don't have to read a user manual. For a complicated task, yes, we have to read a user manual. But typically, we can figure this out. We know by, let's say, common sense even. For a robot, you have to lay it out. You have to have the rules. So there are two ways of doing it. One common way, or I would say the most common way of doing it, is by using a finite state machine. So in ROS, there's a very nice a sub framework, I would say, to implement a finite state machine for your robot. And it is a bunch of rules. Probably you have heard of finite state machines, not financial, finite state machines. Maybe you have heard of it in your studies. It's not only used in robotics. There are many fields that uses this concept. So you have a definition of states the robot can be in and what inputs it can take to change the state to a different one. So that's what happened when the robot realized, using its sensors, that the garbage tank is full. It goes to the state. So it's in the driving state, cleaning state. When the input comes from the sensor saying garbage tank is full, it goes to a state where, okay, clean garbage tank. And then it does something, and then comes after the state is returning, it comes back to the cleaning mode. Very simple scenario. So in the slide, I'm showing you a football playing robot because it's just quite clear and straightforward, and I could easily find it in some, I think it was a thesis, master's thesis of this person. But that's the idea, that's the principle. And this is like the definition of the robot's behavior. And it's a very important aspect. The problem is when you have a dynamic environment with many possible scenarios, this becomes very complicated. There are hundreds, even thousands of rules. And when something changed, you have to maintain this huge code base of many, many rules. It becomes quite hard. Therefore, scientists have been looking at, I would say researchers have been looking at an alternative for several years, actually. This is based on reinforcement learning, especially deep reinforcement learning. The idea is to teach the machine these behaviors by experience and, let's say, a certain value function. I'm not going into reinforcement learning now, but the idea is that you could, instead of writing down all the rules, let it figure out by experience, and a much lower set of ground rules. This obviously is a much better approach, but I have not seen it in vehicles. Maybe there are companies using it, but I have heard of one company that uses robotic arms in manufacturing. They use reinforcement learning to train their robotic arms. I don't remember the name, unfortunately, but I think it was backed by Microsoft. Yeah. and it's promising. I'm actually quite excited about this field of research, and I think that's the way to go because, as I said, writing down all the rules is not possible. There is always a new scenario that you forgot, and then what happens is a problem. But reinforcement learning has a better chance if done properly. It has a better chance of handling previously unseen scenarios also. All right. Right. So when it comes to a commercial product, it's to be used by people who are not roboticists. They are not even people who have good computer literacy. So the user interface has to be very user friendly. And sometimes engineers have to learn it the hard way because engineers, when they design, this is no insult to engineers. I'm also fond of engineers, right? I have seen in many cases when engineers design the user interfaces, they think like engineers, then they assume the end user to also be an engineer, and that sometimes fails miserably. So one way is to actually hire a specialist who knows more about user experience and user interface designing. Or as engineers, you could pay more attention to design thinking. There are many resources you can use, and talking to the user, right? Let them use it and then look at their feedback, see how they're struggling. Don't help them ask why, what's wrong. And it needs usually many iterations. That's actually a critical part of the robot, because when you sell something, uh, this is very important. Usually you sell robots with a trial period, and then there are decision makers, and there are people who actually use the robots in the field. And if the people using the robots on the field are not happy, if they find it difficult to use, uh, then it's a problem for your product, right? I mean, the good thing about autonomous robots is that it has to do most of the things autonomously, but there are situations where people have to interact with it. Yeah, when deploying things. Right. Okay, very critical topic for real life applications. So liability of an accident has to be minimized, right? So first, accidents have to be minimized. The other one is that I think I used the wrong word. The liability cannot be minimized. The probability of an accident has to be minimized. You have to analyze your system for all possible failures. There's no easy way around this part, actually. It's a very time consuming process. You have to make sure your robot does not injure people seriously. That's number one. And ideally, it should not also damage property, because that's a financial loss for somebody, right? So analyzing all possible scenarios. What happens if one sensor goes off or one sensor goes blind? There's a plastic cover flying onto the sensor and does not see that part. Does it then stop? Does it assume there's an obstacle on the blind spot, or does it just move without knowing the sensor is covered? A very important scenario. An easy scenario to happen outdoors, right? Even indoors. There are guidelines. So I have mentioned 2 ISO standards to guide people to make sure certain aspects are met. You have to consider these guidelines in combination with uh, the functionality of the robot. And typically, a robotics company or a group has to take some external consultation on this topic, because it's a specialized field, and robotics engineers are not naturally aware of all the requirements in this area. So yeah, and it's not something you could avoid doing. It's yeah, okay. So what kind of challenges do you meet when you deploy or when you develop such a robot? At a very early stage, you have to one of the earliest problems are the sensor noise. Uh, I mean, for example, lidars are getting actually much better, but even lidars have situations it has issues. I remember once, so when the cleaning robot has to drive into a building from outdoors, I remember once through the glass windows, it made a phantom obstacle inside the building. So the obstacle was not there, but because of the reflection of the LiDAR, the lasers from the glass, the reflection was in a such a way that an imaginary object was inside the corridor and the robot would just not move. So that's a phantom obstacle. And yeah, these things can be handled with lots of image processing, computer vision, but this is sensor noise, right? Ideally, you use cameras or an additional sensor combined with the laser sensor, make sure there's actually nothing there, and then move. So one way of handling sensor noise is combination of sensors, sensor fusion, and the other thing is the quality of the sensors. So usually if you buy a cheap sensor, that's more noise, very true for IMUs, and it's much more processing, much more denoising. So more software development effort. So if you buy slightly more expensive, high quality hardware, you don't have to waste too much time removing noise. So that's point two. But as a company, you have to be very careful. You cannot just buy the most expensive one, right? So it has to make financial sense. Right. So in our case, as a cleaning robot, you have to drive very close to obstacles like walls. And this has a race condition, so to say, with the safety system. The safety system will not let you drive too close if it thinks you are going to crash into something. But to clean something properly, you have to drive very close to things. And yeah, you have to figure out ways around it. Drive close while assuring it's safe. There are so many other problems that can happen due to the dynamic environments. So changes of the map, maybe there's a new wall built, a tree being cut. So in Europe, in autumn, the trees shed the leaves and then suddenly the map looks a bit different. Yeah, weather conditions. I have seen water puddles having reflections that can really cause trouble even to LiDARs, cameras obviously, and also to LiDAR sometimes. Yeah, so these are some of the challenges. I think I can add a few more. For example, so when you keep adding software, when you advance your software to make it faster, it might take more computation time. Sorry, it might take more processor resources, and it will take resources from other processes, right? And that's a problem because then something else will be slower. Or worst case, when you buy a more powerful processor, your power consumption goes high. Then you need maybe you have your electric power circuit does not support this kind of power requirement. You have to change your circuits if you keep adding more load to your processor, right? So while you do research, you have to while you keep improving your software stack, you have to pay attention to this case of changing resource requirements. It's a very important aspect. Yeah, I think that probably covers some of the main things. So to conclude, we talked about the main components of hardware in autonomous utility robots, how they come together. We talked a bit about what kind of sensors we can use and some trade-offs, some limitations. We talked about the main software components like the localization and mapping, the path planning, and the behavior engine, robot behavior like finite state machines, or according to latest research, reinforcement learning. And then finally, we talked about functional safety, which is also a very important area. And now I think I can take some questions. I don't know how it works actually. Can someone tell something?
Yeah, guys, if you have any questions, you can post it in the chat box. So, yeah.
I should be able to see the chat, I guess.
Hello.
Yeah, hello.
Dr. Thanuja, there is a question in the chat box.
Did you ask? Wait. Okay, there are some questions. Okay, wait. So you have, I have one question. Could you tell about? I think this is a time of flight sensor. I don't have much experience. I think it's a proximity sensor. It's a way of measuring the distance or something. But I have not used it, so I will not comment much about it. What are the future research areas in this field? Right. So all these areas like so localization and mapping keeps improving. There are things like, let's say, automatic segmentation of objects in the map already. In path planning, it's not as crowded as SLAM or object recognition, but path planning also is a field that needs some research. And obviously object recognition and detection. As I said, it has to be fast and low resource consuming while being accurate. So it's clearly an area you can work on. And as I said, the deep reinforcement learning for robot behavior is also a nice, it's also an exciting field of research. What else? Anyway, I'll go to the next question. How much collaboration between mechanical engineers is needed for a robot like the one you designed? Well, yeah, you have to have, I would say the team comprises of mechanical engineers, electrical engineers, and also computer scientists. The role of a mechanical engineer is obviously starting from the 3D design. So you have to design components, you have to build certain machinery sometimes, because these are utility robots, right? Imagine a fruit plucking robot. There's this robotic arm. Maybe you have to change some things. There's a grasp mechanism. So obviously lots of mechanical engineering and control going in. So yeah, we had mechanical engineers in our team. Yeah. What are the main differences between LiDAR and 3D camera? Okay, LiDAR is using laser rangefinders. So it's based on laser. 3D cameras are, so there are types of 3D cameras. So a stereo camera, passive camera is something that computes the 3D image based on two separate 2D images. And you have also 3D cameras that project some pattern and then compute the 3D image. One of the main differences, apart from the type of wave is that LiDAR already gives you the 3D coordinate, and the camera, you have to compute it. Sometimes there's a computation module in the camera. Sometimes you have to compute it on the computer. So a bit more resource intensive. Can you give me some instructions to learn robotics technology step by step? Mm-hmm. Yeah, I mean, I could, maybe you could start with the tutorials in ROS. There's a ROS wiki. Maybe have a look. It will tell you the basic things. Yeah. Can robotic enthusiasts from other departments join robotic projects? I don't know about, I mean, I joined recently the department. I don't know how well the interdepartment work goes on. I mean, currently I don't have any robotic projects. I actually currently work on medical applications. At least for now, I'm defining my path now. So for now, unfortunately, no robotics projects from me. But maybe you could check with the others in the department. Maybe Dr. Salochana or Dr. Chandran might tell you more about it. Next question. I'm a computer science undergrad from a private university. I'm enthusiastic in robotics and artificial intelligence. Can I join to work in yeah, I cannot really answer this kind of question. It's more an administrative matter. So I will have to skip that question. Maybe. Okay, I think Dr. Chandana just responded. Okay, so the answer is yes. So people can work with from other departments for things like competitions, hackathons. Yeah, nice. That's good. That's, I think, the way it should be. Robotics is by nature an interdisciplinary field, and so the university I was in Zurich, the Institute of Robotics was made of mechanical, computer science, and electronics. All. So that's the way it should be. Okay. Yeah, it's nice when people work together from different backgrounds. Right. Okay.
Shall I end the session then? Are there any more questions? Okay, seems like there are no more questions. So since we have reached the end of today's session, I would like to thank Dr. Thanuja Ambegoda for dedicating your valuable time on behalf of us conducting such an interesting session on autonomous guiding vehicles. Especially, I'm sure the students on the I stream of CSE department focusing on embedded systems gained a lot of insights today. So on behalf of all of them, I would like to thank you for joining with us today. Then I would like to thank the wonderful audience here today. I hope you all made this an opportunity to gain some new knowledge. With that, I would like to end today's session. Good night and stay safe. Thank you.
Okay, guys, bye-bye. Have a nice weekend. And good luck with your robotics work and all other work also. Bye.
Thank you. Thank you.
Thank you, sir.
Thank you, sir.